Hello students, welcome back. I wanted to complete section 5 in a single video, but I wasn't able to do that. So let's resume. We discussed Jordan canonical forms, and I think we completed discussing J1, but let's do it over. J1 is called hyperbolic case, and that's inspired by the second case, which our textbook author called saddle. When do we have that? That's when we have two different eigenvalues. And the matrix is similar to lambda 1, 0, 0, lambda 2, like this. In that case, you're going to get this expression of matrix exponential by Fulmer's method. E to the lambda 1t times m1, the matrix coefficient here, and e to lambda 2t times m2. Now, these two are different. But if both are positive, like this, lambda 1 and lambda 2, if those are both are positive, then each to the at power will get bigger and bigger and bigger in terms of absolute value as t gets bigger and bigger and bigger because of this. And also because of that. Either way, each to the at will get bigger and bigger and bigger. You see? You're going to get something like this. Why is this so important? Because the trajectory is basically e to the at power times a certain initial condition. So if that's getting bigger and bigger and bigger, that means the trajectory is, the point, solution point is moving away. And then if this is bigger and bigger and bigger, and this is predominantly negative, then the other way around, so big negative. But in any case, in terms of absolute values, moving away from the origin. So that's what positive eigenvalues are all about. Moving away from the origin, x direction, y direction, both of them. Now, how about the third case? In that case, they're both decreasing. Lambda 1 and lambda 2 are both negative, so e to the lambda 1t, that's going to go down to 0 as t gets larger and larger and larger. Same here. They're both going down to 0. So either way, x direction or y direction, or u direction or v direction, they're both merging down to the origin. So we have stability here, stable equilibrium. In this case, unstable equilibrium. How about the saddle case in the middle? One is positive, one is negative. So if this is positive, no, the other way around, this is negative, so going down. So in x direction, in horizontal direction, compress and decrease down. And if this is getting bigger and bigger and bigger, because lambda 2 is bigger, so this is taking place. So vertically, in y direction, move away from the origin. That's basically what happens here. In x direction, decrease, move toward the origin, but in y direction, pushed away from the origin, like this. And these pictures are actually all hyperbolae, so this thing is called hyperbolic. And because this one is so dominant that we usually call the entire circumstance as hyperbolic, even though these two pictures do not really look like hyperbolic. The reason, what if we have 100 eigenvalues, maybe even more? Well, this is for all positive. All 100 eigenvalues are positive. Here, all 100 eigenvalues are negative. Probabilistically, these two cases are relatively unlikely. Most of the time, it's going to fall here in the middle case. Some positive, some negative. If there's at least one positive, then in that direction, things will merge in and then disperse away. So we have unstable equilibrium in the middle. So all negative, then we have stability. Otherwise, all unstable. This one too, this one too. So we went through J1, hyperbolic. Next topic, J2, parabolic. This kind of face portrait. And this is called parabolic. And do they kind of look out parabolae? I'm not exactly sure. in terms of looks. It's called parabolic, and that's when the matrix A is similar to this matrix, lambda 0, 1 lambda, and we have only one eigenvalue, lambda, and one way to get the similarity is having 1 like this. Another way to get the similarity for the double root is like that, 0. And the latter case we have completely linear, because you see, this is lambda, that is lambda, so lambda times the identity matrix actually. This is nothing more than lambda, lambda times the identity. Okay, so basically the same shape, but expanded by lambda or contracted by lambda, basically that's what it is all about. So contracted by lambda or expanded by lambda, lambda is less than 0, greater than 0, and expanded or contracted, they're all following from this behavior. E to the lambda t is getting bigger and bigger and bigger as t gets larger, or vice versa. Smaller, smaller, smaller as t gets larger. And that's why less than 0 contracting, greater than 0 expanding like that. That was a little bit easier case, the linear case. That's why I talked about J3 first. J2, on the other hand, is a little bit more complicated because of this 1. But main idea is the same. We have this kind of matrix exponential by Fulmer's method. And then these two behave the same because we are looking at the same eigenvalues. So increase or decrease either way. So all increasing, no, all decreasing here, all increasing. Lambda is less than 0 or greater than 0. But previously everything is just linear because no change in shape, just straight ahead contracting or expanding from the origin. But this time because of this 1, and then the effect of that, what do you call the transition matrices, we have some curving and tilting, and that's why we have this kind of behavior. We call it parabolic. The final case is elliptic, and this kind of thing. We have rotations, and that's given by complex eigenvalues. The eigenvalues are alpha plus beta I, alpha minus beta I. You see, if you get the, what do you call, the characteristic polynomial, and if it's quadratic, the quadratic irrational, then quadratic irreducible, then we have to have a pair of conjugate complex zeros. So alpha plus beta I or alpha minus beta I, and that'll give me e to alpha t times cosine, e to alpha t times sine. You saw that time and time again in Laplace transform and whatnot, so I hope everybody is familiar with it by now. And e to alpha t part gives you the spiraling in or out, because if this alpha is positive, then exponential is going to get bigger and bigger and bigger as t gets larger, which is this case. Spiral out versus spiraling in. That's coming from this e to the alpha t part. Now, how about sine and cosine? Beta is a angular velocity, so that's positive. That angle is increasing. As t gets larger, angle is increasing. So bigger angle, so we are doing clockwise rotation. And beta is less than 0, then angle is going the other way around. So that's clockwise rotation. Beta is positive, counterclockwise rotation. Beta is negative, clockwise rotation. Alpha is positive, spiral out. Alpha is negative, spiral in. So by those signs, we can completely characterize all those qualitative behaviors. Now, what if we have higher dimension? In that case, there are more than 2 eigenvalues. For example, if you have 5-dimensional case, 5 by 5 matrices, then we may have lambda 1, lambda 2, lambda 3, lambda 4, and lambda 5. And then Some of them may be complex, pair of complex conjugate eigenvalues are there. Some may be different, some may be positive, some may be duplicate. You can have all kind of ramification, one after the other. How do we look at each of those? We can subdivide them by each direction, and then, oh well, in this direction we have rotation, in this direction we have expansion, in this direction we have contraction. We have to look at all those separately. In any case, that's Jordan canonical forms. Now, I have some time left here, so let's talk a little bit about nonlinear systems. Why am I talking about nonlinear systems? It's clearly outside undergraduate level. Well, that's because nonlinear system, especially something like this, happens to be my specialty in research, to tell the truth. That's why I cannot resist. It turns out that even if you have a nonlinear system, we can associate the linear counterpart to have some qualitative that shares. We can create a linear counterpart that shares some qualitative behavior around the equilibrium, as a matter of fact. How do we do it? We simply take a derivative matrix. So if we have a multivariable function, then the derivative is a gradient vector, isn't it? But if you have multivariable and also n variable as well, then we have many components. So we have gradient, one row, another gradient, another row, another gradient. We have several gradients put together and we have a matrix, and that's what we call the derivative matrix. And that derivative matrix plays the role of that A. So even if you have something really complicated, nonlinear system, around the equilibrium, we can approximate it to the linear system, provided that a certain condition are met. And those conditions are, if the derivative matrix has no eigenvalue whose real part is 0, if it is something like that, then it is called a Zener manifold, and you have to take it away. And then we have to consider the unstable manifold and stable manifold separately, and center manifold separately. But that's getting way too deep here. And if nice conditions are met, then we can take linear approximation. So even for nonlinear systems, in many cases, we can bring all those down, at least qualitatively, using the Jordan canonical form. In short, this is quite useful. This thing is quite useful. So we went through phase portrait, and that's what it does, and then we went through Jordan canonical forms. All of these are optional. I'm not going to write any exam problems or anything like that. My purpose is to give you some introduction. My purpose is to give you some introduction toward higher level of mathematics, maybe some inspiration. Maybe I can attract some students for differential equations too, who knows. Okay, that's where I'm going to stop, and we'll meet again for section 6 in a separate video.